Nearly a year ago, I made a video on deriving the Euler Lagrange equation, and I kind of figured it would be a bit of a crime to not show any applications uh, for the Euler Lagrange equation. So this video is going to be touching on three applications. So the first application we're going to go over is a very basic one. So we have an object of mass m, and it is some height above the ground, some initial height above the ground. So its potential energy would be, well, its height will be h, and so its potential energy, V, will be mgh, and its kinetic energy, we'll denote that with T, will be 1/2 mv squared, or we'll be using 1/2 m. Actually, I'm going to change this to an x, or actually a y, because this is going to be the y-axis. So I'm going to have to turn this into a variable, the height, basically. But yeah, so this is going to be the y-axis, this is going to be the x-axis, and yeah, my origin is here. So it's mgy, and my kinetic energy is just going to be 1/2 m times y dot, because that's squared, because that's the velocity, because it's in the y direction. Okay, cool. So now let's write the Lagrangian. The Lagrangian is going to just be the kinetic energy minus the potential energy. So that's mg y minus 1/2. Wait, sorry, my bad. 1/2 m y dot squared minus mgy. So here we'll use the principle of least action. And what that says is that if we have the action, so the action is defined as the integral from t naught to some kind of time t of the Lagrangian with respect to time, and I'm just going to write a prime there so there's no confusion between this t variable and this t variable. But yeah, so that's what the action is defined as, and the principle of least action states that we need to find the stationary action. So to do this, to figure this out, to find the Lagrangian that will minimize or extremize the action, we will use the Euler Lagrange equation. And what that will look like is partial L partial, in this case we're using the coordinate y, is equal to the derivative with respect to time of partial L partial y dot. Okay, so pretty straightforward. So we can take the derivative with respect to y here, and so this will be 0 because this is y dot, so this is independent of y, so we'll just get negative mgy. So what this will be is we'll have negative mg, and this, well, in this case, this is independent of y dot, this is dependent on y dot, so we will just get 2 times my dot when we take the derivative with respect to y dot. And when we take the derivative of that with respect to time, we will get, or actually, you know what, I'll do it in steps. So my dot, and when we take the derivative with respect to time, we'll get my double dot. And we can also cancel the m's here, and hence we have shown that y double dot, or d squared y dt squared, is equal to negative g, which is our equation of motion. So this is something we could have figured out using Newton's laws, right? So the force of gravity will just be negative mg, and we can use Newton's second law, F equals ma, and show that the equation of motion looks like this. So it's a very basic application. It's not really that special. In fact, probably using Newtonian mechanics is probably faster. But in other cases, this is kind of a lot nicer. So now I will show off an example where it is actually kind of nicer to use Lagrangian mechanics rather than Newtonian mechanics. And the example I'll be showing off is the pendulum. So the simple mathematical pendulum. So we have a massless string. Maybe that's a little bit let's lower the angle a little bit. So we have a massless string, and we have a kind of point mass of mass m, and we have some kind of angle of incidence, or really just any angle of we'll call this this kind of the origin, the angle origin. And so we can figure out, so its potential energy, in this case it's T, is going to be 1/2 mv squared, and v in this case is just going to be I'll say that the length of the pendulum here, the length of the string here, it will be L. So the way we calculate the actual velocity is simply L times theta. Or sorry, actually this should be more like S, like the distance, basically. So if we take the derivative with respect to time, we get S dot is equal to V is equal to L d theta dt, or L theta dot. So hopefully that makes sense. So this is how we can express the velocity of the pendulum in terms of just the angle and the length of the pendulum. And the angle is just going to be more convenient to use. So we're going to be rewriting this like that. So we have 1/2 m times L squared, theta dot squared, and there we go. So we have the kinetic energy, and the way we can calculate the potential energy is we just imagine a triangle here, and in its resting position the pendulum will look like this. It will be over here, and so to get the height, so this will be the height, right? It's up here, so the pendulum is up here, it's between here, so this will be its height above the ground, and the entire length will be L, and so we need this height. So we need to do, so we just need to subtract the entire height, this entire height L, by this height, which, I mean, if you know some basic trigonometry, it'll just be L times cosine theta. So the height will just be the total length L minus L cosine theta, or L times 1 minus cosine theta. Although this is kind of unnecessary, but you could also just kind of disregard this one and place the origin up here and just say that height is just negative L cosine theta because it's below this, so it'll just be negative this length because it's negative below that. So you could just write the height as negative L cosine theta. But yeah, so to calculate the potential energy, we just have mgh, and that will be mg times mgl times 1 minus cosine theta. The Lagrangian will be t minus v, and that will be 1/2 ml squared theta dot squared minus mgl, not mgh, mgl, plus mgl cosine theta. And if we apply the Lagrangian, the Euler Lagrange equation again, we'll notice that, so in this case we'll be taking the derivative with respect to theta. So we have dl d theta equals d dt dl d theta dot, and so this will just be, so this will just be, all of this is independent of theta, right? All of this is independent of theta, only this is dependent on theta, so we'll have just negative mgl sine theta. Okay, and then this will just be, so this is all independent of theta dot, so this will just be m L squared theta dot, and that's it. And we can cancel the m's, we can cancel an L here, so get rid of that square. And if we take the derivative with respect to time again, on this side, because we have to, we will end up with, and then if we just divide by L, of course, we will end up with d squared theta dt squared is equal to negative g over L sine theta. And this is the equation of motion for the simple pendulum.